Let me first thank the organizer for organizing this conference and for inviting me here. I see a lot of familiar faces, some of them I haven't seen in quite a while, so I'm very happy to be here. And this is supposed to be happy hour time. It will be an hour. I don't know if it will be happy, but so what I want to talk about is a work that has appeared on Monday, actually, and it's a work that I've done with Sergei Dubovsky and Massimo Porrati, both at NYU, and I will also mention some work in progress with them and with Riccardo Borsato. And I will be talking about this procedure, which I call topological gauging, which is a way to rewrite a large class of deformations of quantum field theory, deformations which are performed using concept currents. Definitions later. So I will first talk in general about the formation of quantum field theory and the point of view of the space of theories, which is the point of view that I always keep in mind when thinking about these, and also give some motivations for this and for the study of this kind of theories, of these deformations. And then I will define what I mean by double current deformations, and then well, double current deformation they can be distinguished in two classes, one where the currents are abelian and one where the currents are not abelian. And we were able to define a procedure which we call topological gauging, which essentially is a proper quantum definition, full quantum definition of this deformation, both for the abelian and for the non-abelian. I will first concentrate on the abelian case and show how to compute the scattering matrix. And then I will give some example, well, a very simple example of a double current deformation, and well, present its equivalence with a TST transformation. And then I will mention something about non-abelian currents and how they relate to Yang-Baxter deformation, and finally how TT-bar deformation enters this perspective, how it's related to centrally extended Poincare. If anyone has any question, just stop me. I will try to be as light touch as possible, but you know, questions are welcome. So, yeah, let's start with deformation. One point of view to study QFT and their deformation is to study the vicinity of an RG fixed point. So we take a CFT. In general, we can study this in any dimension. And then we can move out of the CFT point with three different ways. So we can either move out with a relevant operator, with a marginal one or an irrelevant one. Now, these three statements, for relevant, marginal, and irrelevant, are classical statements. They need to be corrected when we go to the quantum level. So this is just a reminder. I'm actually supposing that marginal operators here are truly marginal, and put the marginally relevant and marginally irrelevant in the other classes. So what can we say about this kind of deformation? When we deform a CFT with a relevant operator, then we know that the theory that we get is a UV complete theory. This is quite simple. We have a UV fixed point. The operator is important in the UV and become less and less important as we move towards the IR. So this can be really considered as the UV CFT perturbed by a relevant operator, and then when we flow to the IR, nothing bad is supposed to happen. If we instead use a marginal operator, then what happens is that the importance of these operators don't change along the RG flow. So what we are defining, if we start with the CFT, is really a conformal manifold. We have a family of conformal field theory, which are parameterized by these couplings here. And instead, what I think is the most interesting case is when we try to do the same game, perturbing a CFT, or for that matter, any quantum field theory, with an irrelevant operator instead. Then what happens is that this operator, when we flow to the AR, becomes more and more important. So, sorry, becomes less and less important. It becomes more and more important if we try to go to the UV. So what this means is that if we go out of the CFT with one of these, say with a small parameter, and then we turn on the RG flow, trying to flow towards the UV, then the flow will escape from the CFT and will just go somewhere. In general, we won't have a UV fixed point. The theory will not lie in the space of local field theories. There are a lot of things that can go bad. And in general, this theory defined like this, is has to be treated as an effective field theory, and there is an inherent length scale past which the theory stops being predictive and all the usual thing that we know from RG. And one thing that I like to underline is the fact that we are in d bigger than or equal than 2, we always have a finite number of these operators, but these operators are always infinite in number. So if we want to study the space of all the possible field theories, if we want to explore that space, then we need to take in account the presence of these irrelevant operators. This is one of the reasons why I'm interested in this class of deformations. Now, one setting where it's useful to work when studying deformation is that of Wilson and Kogut, is to consider the space of quasi-local field theories. So this is a space, each point in the space is equipped with an action, and the action is equipped with a UV cutoff in general. The UV cutoff represents the length of the probe that we use to look at our theory. So we decide to look at our theory at a certain length scale. Now lambda here is a momentum, so it's the inverse of the length scale. And the quasi-local here means that these actions that are defined as the integral of a local density, and the local density can be a polynomial, it can be also a non-polynomial function. In general, this theory will display some non-local feature. And the only thing that we ask of these theories here is that the non-local feature are restricted in a range which is smaller than the one that we use to look at the system. Now, what happens when we do RG on these kind of theories? Well, in this setting, an RG is a variation of the length scale, so it's d over d log e of the action, and this variation is controlled by a vector field. Now, we can think of this space somehow like a manifold. It's not properly a manifold, it's a more complicated structure, but it does possess a tangent space, and the tangent space really is nothing but the space of the fields of the theory, because the tangent space is the space of direction out of a point, and we exit from a theory by deforming it with a certain operator.
But why local operator? I could imagine a bigger tangent space when I deform with non-local operator.
Yeah, here we're talking about local operators. Yes. Yeah, I don't know. But yeah, but that might be an interesting concept. So here, yeah, they are local operators. Now, when we try to move towards the IR, as everyone knows, there is no pathology which is expected. And the reason is that this procedure, when we go to the IR, essentially amounts to integrating degrees of freedom. So we already have the degrees of freedom to describe the theory at that length scale and the larger length scales. So nothing bad should happen. But on the other hand, if we try to go to the UV, we might encounter a situation where we need more degrees of freedom, and so we do expect in general pathology. Also, you can see it, if we try to increase the length scale, we might encounter this non-locality range, and then at some point the theory will just lie outside of the space. So in other words, there is an intrinsic UV scale such that the theory doesn't lie in this space when the momentum is bigger than this intrinsic scale. And then, of course, there are UV complete theories. There are theories for which this momentum scale is infinite, so we can actually describe it at any length scale without any problem. Pictorially, we have something that looks more or less like this. So we have, for example, a CFT. We deform it with a relevant operator, and then the CFT in general will either flow to a CFT or an empty theory, an isolated point, or it might flow to another conformal manifold. We might move on the conformal manifold with some irrelevant deformation. And in general, if you try to move out of the theory with a flow that is controlled by an irrelevant operator, then what we are doing is actually, well, technically it's like going towards the UV, and then at some point we should go out of the space of theories. Now, one thing that was found out in 2016 is that if we try to deform our theory, now I'm moving to 2 dimensions. If we are in 2 dimensions and we try to deform our theory with a very specially relevant operator, which is called TT bar, and I will define it in a moment, then we do observe the same situation. We do go out in some way of this space, but this theory is controllable at any length scale. We can find answers, or well, observable for our theory at any length scale, even here, where we are supposed to go out of the space. So this deformation gives us a chance to try and understand what lies out of the space, what are the features of the theories, and the feature of this theory, one of the features that it's interesting, is that these theories will be non-local. So they might have something to say about gravity and theories that are non-local. And yes. So the TT bar flow, the TT bar operator, is this operator here. It's nothing else but the determinant of the energy momentum tensor. And the TT bar flow is a flow which, well, it's a you take any action at alpha equals 0 that you want, and then you define a family of actions such that this identity is satisfied. Now, this is a classical equation, of course, but the fact that this is the energy momentum tensor, it's a conserved quantity, allows us to control also the quantum corrections to this classical equation. That's because this is a well-defined operator at the quantum level. Through point splitting, we have control on all the corrections. They are all essentially derivatives of local operators, so they don't matter when we take expectation values. This means that we can take that, put it in a path integral, and then compute stuff. That's the important fact. Now, as I mentioned, this is a deformation which is irrelevant, but it's still controllable at all scales. So, well, actually, it's something like solvable, in the sense that we can take unobservable, for example, the energy spectrum on a cylinder, infinite size, a cylinder of radius r, and then the energy at any energy, n is a label for the excited states, for any state, where it labels the state, the energy satisfies the Burger's equation, which is written here. This is an equation that appears in hydrodynamics. It describes the wave breaking in that setting. And in this setting controls the profile of the energy as a function of r, and the momentum, of course, is quantized, so it cannot depend on alpha. And what happens depends on the sign of alpha. So this is a typical ground state profile. We have some bulk energy here, and we have some CFT behavior at small r. And depending on the sign of alpha, we either have the formation of a square root singularity, or we have a situation where the energy doesn't go to zero, doesn't go to infinity, sorry, when r goes to 0. So this situation is already quite interesting. This is the same kind of phenomenon that we observe in string theory. This is a Hagedorn transition. If we take this ground state and we compute the density of states at high energy, we see that they grow abnormally fast, in the same way as they do in string theory. So it seems like there is a relation to string theory, which I will comment in a moment on. And in this situation, this is perhaps even more puzzling, because what this says is that we really are looking at a system that has a finite number of degrees of freedom. And that's because we get to a constant at r equals to 0. Now, the interpretation of this was given, one interpretation of this situation was given by Mezzei, Magog, and Verlinde, and they suppose, well, they say that this kind of flow should be really looked up in the setting of, in a holographic setting. So we have this field theory that lies on the boundary of ADS, and the boundary is at infinity. But what happens when we do the TT bar flow with this sign is that the boundary is pushed towards the bulk. And now we have a finite size, a finite distance from the bulk, which means that we have a finite number of degrees of freedom, which is the largest given by the largest possible black hole. So that's an interpretation.
What is alpha?
What? Alpha is the deformation parameter. Is this one? This alpha. And another thing that you can compute is the S matrix. Now, this is the two-particle S matrix. There exists a similar formula for the n-particle to m-particle S matrix. Everything that happens is that the deformation is contained completely in a CDD factor. This is a factor, is a pure phase factor that depends only on the energy and the momentum of the particle which are involved in the scattering process. And the general formula was given by Dubovsky, Gorbenko, and Mirbabai. This was found for the two-particle scattering in our article in 2016. Okay. So this theory is interesting for various different reasons. Well, first of all, it's a universal deformation. You can take any theory, as long as it has an energy momentum tensor, you can define this deformation. It doesn't need to be integrable, it can be whatever theory you want. And what was shown in a large number of articles from various different perspectives is that it's very closely connected to string theory. One way to see that is you simply at the classical level, you take the free boson, you do the TT-bar deformation, you solve that equation for the action, and what you find is the Nambu-Goto string. So this was shown in this article. And so this is just one aspect. The other one is if you compute the spectrum, the energy spectrum, you find the same Nambu-Goto spectrum, so there is really some kind of connection with string theory. There is also connection to quantum gravity, and this is seen both at the classical and on the quantum level. At the classical level, you can define the deformation equivalently like a coordinate transformation that couples the geometry of your system with the energy and the momentum of your system, which is very much similar to what happened in gravity. And in these two articles, these gentlemen, they showed that the TT-bar is equivalent to a coupling to a JT gravity setting, to a, JT gravity sector, Jakiv-Teitelbaum, so some kind of topological gravity into dimension. So again, we see a connection with gravity. And then another thing which is very interesting is that these deformations allow for a number of generalizations. So one way to generalize is to take the deformation of the S matrix as a definition and to substitute, instead of having the phase factor that I showed you before, a generic CDD factor. Now this CDD factor can be constructed from higher spin conserved current if my theory is integrable. It can also be constructed from other conserved current, and we will always get some kind of phase factor like that. Now, these kind of S matrix were studied by Zamolodchikov and Musard and Simonetti, and they also appeared in the study of the effective string description of QCD in the works of Dubowski, Flogger, and Gorbenko, and Caselle, Fioravanti, Liozzi, and Teteo, and a number of other works. Now, the perspective that I'm going to take will not be this one, but instead I will be defining the double current deformations simply by taking the flow equation that I gave you before and by using two arbitrary currents instead of T and T bar, or, well, T mu nu and T rho sigma. So I will concentrate on this. There are a number of articles where these J's are actually higher spin conserved currents, which are these, but I will concentrate in the case where these are U1 currents, or in general, non-abelian currents. And so our theory need not be integrable in general in order for us to define these. Okay. So this is the classical definition that I will be starting from. It's the same one as before, but here I have two currents. I suppose that the two currents are conserved, so they satisfy this continuity equation. And in virtue of that, I can repeat the same argument as for TT bar and to say that this is a well-defined operator also at the quantum level. I have full control on the OPE of these currents, so I can do quantum theory with this action. Now there is a slight problem, which is that this equation, the continuity equation, in general, it's only true when alpha is equal to 0. If you take this current and if you take this definition and you try to compute even perturbatively the first or the second order, you will see that this current won't commute anymore in general. They will commute only if they are abelian, or if I generalize that formula and I put an antisymmetric tensor there, this arg, then I can impose the commutation relation only if the inverse of R, so R need to be invertible first of all, and the inverse need to be a 2 cocycle.
Can't you change JA? I mean, in the continuity equation by some linear term in alpha or higher terms in
so
alpha?
we tried. So there is one deeper point of view, which is that what you're doing here, you're messing with the symmetries of the system, and it will be a bit clearer when I explain what the topological gauging is. And what happens if you don't choose this, then you will completely break the symmetries. So the current will disappear. It won't be there anymore. I mean, maybe there is some non-local transformation. That might be, but some simple-minded linear combination doesn't work. All right. So I will concentrate on the case where R is actually an epsilon tensor and these are abelian current for the moment, then I will return to the abelian case later. Now, one of the goals of our work is to take this definition and to make it into a full quantum definition, so without having to refer to the classical action. And the point, well, the future will be to actually not even refer to actions, but to define only to observable directly without the need to have an action. But let's start with the with this setting, and in order to define the current invariantly without having to do the Noether theorem to compute the currents, we can define this current simply as the response of the system under the variation with respect to a background gauge field. So what we're doing here, we are introducing with a minimal coupling a gauge field, and then the currents will be defined by this variation formula. Now with this equation here and with the flow there, we can do a first order analysis. And so we see that infinitesimal for alpha very small, this difference is simply this wedge J operator. And this we can treat it on the exponential with a Hubbard-Stratonovich transform. So this is where we introduce our background gauge fields with this antisymmetric. This is some sort of antisymmetric mass term or something like that. And now the last thing that we need to do in order to rewrite this in terms of the action is to use this first order formula for the variation with respect to the gauge field. And then when we substitute in, we get this formula here. Now this is valid only at first order in alpha. But the point is that what we did is to take this and make it into a definition. So we suppose that, we define an action alpha from this path integral. And then what we proved is that this action A alpha classically reproduced the flow equation that we started with. And this is very easy because this is a simple saddle point computation. You fix the value of alpha through the saddle point, and then you substitute in and you try to prove that this action solves the equation. You do some algebraic computation and you show it. So this works as a quantum definition for the flow that I showed you before. This is actually not entirely satisfying, and the reason is that we would want to have conserved currents. Now here at this level, we would need to impose the conservation of J by hand by saying that A is flat, because in principle we're integrating over all field configuration for A. But in order to cure that, we do a simple change. We introduce a Stuckelberg X. And now the Stuckelberg immediately imposes the flatness of A. That's everything that it does in this situation. And additionally, it also grants gauge invariance to this path integral. So this is the definition that we're going to use. Now, at the level of computation, it doesn't really matter if X is there, because you always do more or less a saddle point, so you can always forget about it. And in fact, for example, let us suppose that we are in an empty and featureless space. So what we're going to compute now in this slide is the partition function on a plane. We have no insertion, there are no topological obstruction. So this means that A, since A is flat, A needs to be exact. Now if A is exact, it can be, well, I can fix X to 0 by gauge choice. I just substitute everything inside, and then I see that everything that happens is that the fields, the fundamental field, rotate with some Wilson line in this way. And then if I just change variable inside the path integral, I get the same answer. So this means that these deformation, they don't do anything to the partition function. So the system, if there is nothing, if there is no spectator, there is nothing that the deformation can latch on. However, the situation will change when I compute something more non-trivial like the S matrix, which I will do in a moment. But before doing that, let me extend slightly on this, and let us suppose that the symmetries, I have two currents, two U1 currents, and let us suppose that these two symmetries are anomalous. They have either an anomaly or a mixed anomaly. Now, in this case, in principle, we cannot do what we did here, but there is an easy way to cure this. We have an anomalous transformation under a gauge transformation in this way, where this C encodes the anomaly. And there is a simple way to cure that, and simply to introduce. We can do that because we have an integration over the Stuckelberg already. So the anomalies can be eaten up in this way, and we can work as if there was no anomaly. However, there is one point which, oh, sorry, plus minus, it should be a minus, but it doesn't matter. There is only one point that changes, which is when we compute the saddle point for the Stuckelberg, we get this equation here. Now before, we only had this, and this is an equation that imposes the flatness of A. But now this matrix can be singular, and this singularity cannot be eliminated in any way, so it needs to be something physical. In particular, I have isolated points, in general 2, AC, for which I cannot define this deformation. And in order to see that, we can look at a very simple example, which is the compact boson. So in the case of the compact boson, we have two currents, which are the two natural currents, the shift and the winding current, defined in this way. And it is well known that these two currents have a mixed anomaly. The way to see that you do a minimal coupling in this way, from this you can recover the current, and doing a gauge transformation on BW, you can see that there is an anomaly. And I will write it in a moment. From this you can also do the saddle point that I showed you before to find the deformation, which is simply this. So it's the same exact theory, only with a deformed radius in this way. Now notice that alpha equal to pi is a singular point. Now the matrix of anomalies is given by that. You just shift BW to find this. You find that there is a 1 over 2 pi. And if you compute the singular values, like before, you find that alpha c is exactly equal to pi. So the singular values have a physical significance, and in this particular case, they correspond to points where the radius of the compact boson blows up.
So was it an exactly marginal deformation?
It is an exactly marginal deformation, yes. So this is a parametrization of the conformal manifold of the compact boson. Okay. Now let's return for a moment to the non-anomalous case, and let me try to compute the S matrix. Now in the situation, instead of the one that I gave you before, where I was computing the partition function on a plane, it's different because we have insertion, so we have topological features, which are the particles of past infinity and future infinity. So what we can do is that we can follow the same idea that we had before. So rewrite the integral by doing a change of variable of the fundamental field by this phase factor given here. This psi is just the integral of the Hodge of the current. And then these gamma, since J are conserved, I can choose this gamma as I want. And in order to, well, to stick with the time evolution of my system, I'm studying particles that evolve in time. I fix it on a constant time slice, and I fix the end point of my line to be minus infinity. Now, if I do so, and I try to compute what this does, I see that this operator psi a measures the number, the total charge which lies to the left of the point x, and it subtracts the total charge that lies to the right. So it's an operator that measures the difference of charges on the two sides of a point along a constant time line. Now, since I rotated my operators, my fundamental field, I need to rotate any operator that I want to consider. So in particular, I need to rotate the in and out operator. And if I do so, I get this phase factor in front. And then I construct the in state by just multiplying operator from the left. I do commutation, and what I get is this phase in here. Now, the S matrix is just a sandwich of in and out state. The out state just behave in the same way. So I get that the S matrix is just the undeformed one times a phase factor that instead of being depending on momenta, here depends on the charges of the U1C. So it's exactly the same thing that happened in TT bar, it's just slightly simpler. And like this, we can compute partition function on a torus. In principle, we can compute correlation functions and things like that. It's just a geometric way of computing the things. Okay, so now let me do an example. Everything was kind of abstract. So the simplest example that we could find that is non-anomalous, the other one was anomalous, but this one is slightly more interesting even though it doesn't have an anomaly, is the case where I have two complex bosons and I use as symmetries, as current, the phase rotation symmetries. Now this phase, I can parameterize the fields in polar coordinates. It will be easier in a moment. And in order to define the deformation, I do the usual, well, what I showed you before. So I do a minimal coupling, which is very simple, looks like this. And then I plug inside this expression the solution to this equation here, which is just a saddle point. Here I'm doing the classical analysis of this theory. And if I do so, what I find is this action here. This is written for a variable because in complex variable it will be a mess, so it's much more easily seen in this variable here. So some of you might recognize from this denominator, this looks like a TST transformation, and it actually is a TST transformation. And in fact, you can suppose that this is a linear sigma model. Well, it's a linear sigma model actually, but it's a sigma model with this metric here, and this is a sigma model with another metric that you can compute easily, and the two metrics are related by a TST transformation, which is the sum of a T-duality, which is simply so here you have two U1s, two circles. You invert the radius of one of the circles, essentially. Then you do a shift on the other, which depends on this theta, and then you do a T-duality back in theta 1. And what you get when you do this on the metric is exactly this metric here. Now, this is nothing new. This is a model that was proposed by Lunina and Maldacena. It's actually quite famous. But what it means in this context is that there is an interesting thing here, is that if you look carefully at this is a CFT, it's a non-compact boson, but these operators here, they are not operators of the CFT because they have a naked boson here. So they don't have the correct Weitmann functions. So in principle, these are not operators of my theory. Still, if I do this J with J deformation, my deformation is still a marginal deformation, which is kind of strange at first. And it is marginal because we know that the TST preserved the conformality of my theory. So, yeah, well, this is something that interested us. And the first approach that we had was to go and study the Weil anomaly equations in loop expansion, and we found that up to two loop, they actually, the theory can be made to be invariant under conformal transformation. You need to add quantum corrections. But the fact that this is a TST ensures us that this is truly a marginal deformation. All right. So, I will move to the non-abelian case now. I will simply mention something. The non-abelian is simply defined with an R instead of an epsilon, and we can do the same procedure, follow the same step that I showed you before, and what we get as a quantum definition is this expression here. It's slightly more complicated, but it really says the same thing. It's nothing different. And the difference here is that I get an omega here in here. So if I have a symmetry which has a non-trivial omega, which is not simply epsilon, then this will be more complicated. But really, it's the same thing. And also note that I cannot do this for all symmetry groups. If I have SON, for example, there is no non-trivial cocycle, so this I cannot do. I only can do it in situation where I have a non-trivial cocycle, which in turn implies that I can only do it if my symmetry algebra admits a central extension, because two cocycles are in one-to-one correspondence with central extensions. Now, these formula appeared before in the works of Borsato and Wolff, and they named it as a deformed T-dual model. This is really the same thing as a TST deformation, but for non-abelian symmetries. And what they showed is that these deformed T-dual models are nothing else but Yang-Baxter deformations of the starting action. So Yang-Baxter deformation, you can also show it if you take the definition of a Yang-Baxter deformed action, you compute the variation with respect to the formation parameter, you find out that it can be written in terms of currents in this way at a classical level. So these seem to be consistent. This is still a work in progress that I'm carrying on with Borsato and with Massimo Berratti and Sergei Dubovsky, but it seems to be consistent at the moment. And the reason why it's called Yang-Baxter is that the two cocycle, the inverse of the two cocycle desire satisfies the Yang-Baxter, classical Yang-Baxter equation. homogeneous one. But it seems like this action, A alpha, well, okay, no, Young-Baxter deformation with inhomogeneous R matrices, they seem to satisfy this same equation. This is also something that we are looking at the moment. I don't have anything more to say than that. All right. And now, what I would like to close by showing how TT-bar enters in this game. Because up until now, I've been talking about marginal deformations, although it's, well, the fact that these deformations are marginal is still not completely settled, but some of them at least seem to be. But TT-bar is an irrelevant deformation, so it seems to be different. It's a different kind of deformation. But actually, it can be studied in the same way. And the way to see that is that well, first of all, in 2 dimension, the Poincaré group admits a central extension. So there exists a trivial, admittedly, because this is simply an epsilon tensor, central extension. So we can think of following the procedure that I showed you before, and in order to do that, we should really work in first-order formalism. So we should treat ISO2 as if it was an internal symmetry, work everything out, and then impose the spin connection metricity in order for, well, to specify that that is actually a space-time symmetry. But if you do the computation, you will see that the spin connection actually drops out of the computation, so there is nothing special that you need to make. You can just write exactly the same formula as before, but now you will get this expression here, where X is the Zuckerberg and E is the tetrad, and this is the same expression that appeared in the work of Dubowski, Gorbenko, Hernandez, Chifflet. This is a JT gravity term. It's just slightly reworked, but it's just that. So what this is saying is that you can consider, so this is TT-bar essentially. This procedure gives you a TT-bar deformation. And what this slide is saying is that the TT-bar deformation is nothing else but a central extension of Poincaré algebra, or at least can be reinterpreted as a central extension of Poincaré. Now the central extension of Poincaré is the symmetry of non-commutative Minkowski space-time. Now this seems to resolve also some long-standing question that we had, which is that in 2007, so almost 10 years before that TT-bar became a thing, Gross and Lechner computed the S matrix of a free boson in a non-commutative space-time, and they found out the same scattering matrix that we found in TT-bar. But then it was quite unclear where the non-commutativity of this theory is from. No one really understood that. And the reason really is this one, is that there is an alternative interpretation of TT-bar, alternative also to gravity, which is simply a deformation of the symmetry. There are also some results in correlation function which came out recently. And yes, so this is it. As an outlook, there are a number of things to be done. Well, one of the things that I will be what I'm interested in looking at is how to fit the higher TT-bar deformation in this setting. So supposing that here I was considering internal symmetries, standard internal symmetries of quantum field theories, but if we have an integrable field theory, we have all these higher spin TT-bar, well, energy momentum tensor, let's say, and it's kind of unclear at the moment how to treat them in the same way that I showed you. Probably it has to do with some gauging of Virasoro subalgebra. It will be probably related to higher spin gravity. This I am not sure of that, but I would like to understand them so that everything fits in the same frame. Another interesting thing is that in principle we can extend to non-invertible and discrete symmetry because we can just forget about the fact that we have currents and take as a definition the change of variables with some Wilson line. Now, the Wilson line doesn't require us to have a current. We only need to have a charge, really. We can define the Wilson line also for discrete and non-invertible symmetries. And so we would like to look at what happens when we do something like that. Extension to higher dimension has haunted the people working in this subject for a long time. It's very difficult to extend TT-bar and this deformation to higher dimension. Well, I mean, in principle, it's not difficult to define them, it's difficult to study them because you always lose something. You lose solvability, you lose some properties, things don't work as nicely as in 2 dimension. There are a number of ways that you can do. You can just do the same thing with some more complicated wedge products like that. And of course you won't be able to do exact saddle point, so I'm not sure how prove this will be. I don't know exactly what the non-abelian case will be. And another way to do that is to take the definition as deformation of symmetry. So we define our deformation by taking a symmetry and deforming it in a similar way as the one that I showed you before. That's one other possibility. And also one thing that might be funny to try is to try to break the conservation law in a weak way and then try to do some perturbative analysis on the theory on phi. Now this should be controllable. You have a well-defined starting point, and then you can try to look at first order or second order in this parameter phi to see what happens. In theory, well, if you start with the marginal deformation, you will probably have something that is not marginal anymore after you differ in this way. So maybe that's an interesting path to follow. And so this is. Thank you very much.
It's a case of TT bar deformation. So you have shown that this deformation modifies the spectrum of your model.
Mm-hmm.
So now you have U1, imagine you have U1 conserved charge, and you introduce this modification, so the charge is conserved. So you don't break conservation of U1 charge in this deformation.
Yes.
Now imagine if I will be discussing modification of the spectrum. If charge is conserved, and I classify my states according to that charge. Yeah. Since it's conserved, nothing changes. Yeah. So what's the meaning then of the deformation? What actually does on your theory?
Yeah, so this is a difficult interpretation problem, I have to say, because in principle, all this deformation, they take your spectrum and they move it in block, because they don't change the generation, they don't do level crossing, nothing happens. It's simply the levels are shifted in some way. But if you do TT bar, then you see, and this is result of, I mean, it can be result of numerics, it can be result of exact formula from that Burgers equation. You really see this happening. So this happens because you're working on a cylinder. So what really is happening here is that the radius itself is getting redefined. So you can have, you can picture the spectrum that is, let's say this spectrum, for example, by simply redefining R. You have the same exact spectrum, but now the radius will depend on the energy of the system itself. So in some sense, there is a way in which this deformation doesn't do anything at all to your theory. But you need to redefine all your generators of symmetries, everything in your theory, in a very non-local way. And this was shown by Monica Guica. She showed, for example, that if you take a CFT and you do TT bar, then you still can define a Virasoro algebra. Now, the Virasoro algebra will be a complicated, each operator will be a complicated function of the original ones, which depend on fields and whatnot. But it seems to be there. Now, the extent to which these effects are, well, these effects are physical. We cannot deny the fact that they are physical because they are there. But they can be read in a free way. I mean, there is this, Sasha Zamolochikov told me once that if you take any theory, there is a non-local transformation that makes your theory free. You can just define it. And now this doesn't mean that your theory is free, really. So this is somehow the same situation. But as well, returning to your question, I don't have like a sharp interpretation of what's going on, because what you say is true, but this is also true. So it's a bit puzzling to me at the moment.
But in a finite, you showed that the S matrix changed, no?
Yeah, the S matrix changed.
If you go to a finite volume, then the momentum quantization will be different, asymptotics, beta ansatz will be different, energy will be different.
Yeah, but in fact, that's the point. I mean, the theory is clear.
It's also true for the current deformation.
It's also true, even though it's much less, it's a constant phase shift in that case. But yes, it's true. Yeah. I mean, the difference is there. But what he says on a principle level, it's also true, because everything, all the symmetries are preserved, all the levels are more or less preserved. So yeah, to me it's confusing because I clearly see the effect of the deformation. You can compute them and they are there. But if you just think at what happens to the spectrum, it seems like, I mean, it just gets shifted.
Is it is it possible to do these deformations at the Hamiltonian level? The Hamiltonian?
So yeah, I think this is the path that was followed by Monica Guica, for example. So if you take this and you just write it in terms of Hamiltonian, it's the same deformation with the minus in front, right? So it's simply that. So you can just write an equation for the Hamiltonian. Now, if you want, you can go and look at how the Poisson structure is deformed. And that's where she worked and redefined the field variable in order for the Poisson structure to be preserved, but then the field will be complicated functionals of the other field. So that you can do, yes.
I have a question that is related to
Yes.
Zoli's question. So, if you do TST,
Yes.
then at the Hamiltonian level, it's more or less like change of boundary conditions. That depends on your charges.
Okay.
So, in your formalism, there is somehow you relate the TT bar and current square deformations.
Yes.
So, can you also understand TT bar as some sort of change of boundary conditions that depends on fields?
Well, as far as I understand, the fact that it's related to TST, it's not something that we discovered. It was actually shown first by Apollo and so on. I forgot to mention them, but yeah. They showed that the TT bar and the JT bar deformation were used U1 current and one PC tensor. This can be written in terms of TST in the supergravity background. In particular, the JT bar takes one direction, which is on S, and one direction, which is on ADS. So one will be a U1, and the other one will be like a space-time symmetry. And yeah. So your question was about boundary conditions, or?
Yeah, can you hide everything into changing the boundary
I
conditions?
think so, yes. I still don't know. This is what we're working at with Riccardo Bersato, is to actually derive observable of TT bar or J squared or whatever, starting only from this kind of deformation of the symmetries, or equivalent to the Greenfield twist of the operator. This sort of thing. Yeah, we are working on that. So at the moment we don't know, but in principle it should be possible.
Any more questions? Let's thank Stefan again.